All right, so gases segment 2. So in segment 1, we were looking a lot at the theory, and now in 2, we're going to start looking at some of the math. So the first thing we're going to start off with is Dalton's law of partial pressures. It sounds complex, but it's actually a very simple um, formula to follow from the math side of it. So the total pressure inside a container is equal to the partial pressure due to each gas. The partial pressure then is the contribution by that gas. So if you think of it this way, if you have a room with 3 or 4 gases in it, then all of those gases are contributing to the overall pressure in the room. So P total would be equal to the pressure of each of those individual gases. So for instance, if we're thinking about air, the biggest component would be nitrogen. So P1 might be the pressure from just the nitrogen itself. And then P2 would be just the pressure of oxygen. And then finally the pressure for 3 might be the pressure of CO2. So that's it for the partial pressures. You just simply add up the pressure of each gas and that's going to equal P total. So again, conceptually, if I have 4 containers here, the first container would just be, green gas, second container is orange gas, third container blue gas. And I look at the pressure for each one. The first one comes in at 2 atmospheres, the second at 1, and the third one at 3. So if I just think about this logically, now I want to take all those gases and put it into the 4th container. So we have all of the green, all of the orange, and all the blue that were in the first 3 containers are all now in this 4th container. The pressure then should just be the summation of that. So 6 atmospheres, right? So 2 plus 1 plus 3. We can find out the pressure in the 4th container by simply adding up the first 3. Now, of course, on your exam, it's going to look more like this. What is the total pressure in a balloon filled with air if the pressure of the oxygen is 170 millimeters of mercury and the pressure of nitrogen is 620 millimeters of mercury? So here we just want to pay attention to those units. We want to be in the same units because we want to add these together, right? So we're going to take 170 millimeters of mercury from the oxygen. We're going to add it to the 620 millimeters of mercury from the nitrogen. That means the total pressure then should be 790 millimeters of mercury. I know it just seems too easy. I get that. All right, let's see if we can make it just a smidge harder. In a second balloon, the total pressure is 1.3 atmospheres. What is the pressure of oxygen if the pressure of nitrogen is 720 millimeters of mercury? Well, don't forget, you'll have this with you. 760 millimeters of mercury is equal to 1 atmosphere. Now I just need to decide what unit do I want to be in to answer this question. And so I'm going to pick atmospheres or millimeters of mercury. Doesn't matter which one we pick. These are my 2 conversion factors. We've seen this before. Right? If I want to answer in atmospheres, then I'm going to take the 720 and I'm going to convert that into atmospheres. If I want to answer in millimeters of mercury, then I'm going to take the 1.3 and convert that to convert that to millimeters of mercury using the 760 millimeters of mercury over 1 atmosphere. So in this case, I'm going to convert everything to millimeters of mercury. So I'm going to take 1.3 times the 760. That's going to give me 988 millimeters of mercury. Now again, don't forget those pesky sig figs. How many sig figs do we get here? Well, the 760 to 1 is a conversion unit that's considered exact. So it's the 1.3 atmospheres. Tells me I can only have 2 sig figs. So I'm going to turn the 988 into 990. And then of course I'm going to subtract the nitrogen, which was 720, which means the oxygen then has to be 270 millimeters of mercury. So again, they don't get much harder than that. Just keep track of your units of pressure and make sure you're in the same unit as you do the summation. All right. The next thing we want to look at is Boyles Law. Now, Boyles Law tells us that at constant temperature, pressure and volume are inversely related. So remember, as one went up, the other has to go down. Okay? Now, mathematically, what we can do then is say that P times V is equal to kappa. And kappa in this case is some constant, but we really don't care what kappa is because it's not going to help us this way. All right. What's going to be better is this. If I change the pressure of the gas, kappa, the constant, has to stay a constant. So if I change the pressure, the volume has to change in accordance. That means what we can do then is plug in some scenarios. And the equation we use is called P1V1 is equal to P2V2. All right, so remember both of these would be equal to that kappa, but kappa doesn't matter. We could care less about kappa. Now kappa will change for each gas, which is why it's really useless for kappa, where you only need it for the math so that we can set scenario 1 equal to scenario 2. That way we know if we change the pressure of this gas, its volume will change. If we change the volume of the gas, then its pressure will change. Okay, so we can figure out which one is going to change to which feeling. So what's the questions look like? A balloon is filled with 25 liters of air at 1 atmosphere of pressure. If the pressure is to change to 1.5 atmospheres, what is the new volume? So again, we're going to say P1V1 is equal to P2V2. Now I like to manipulate things as letters, so I'm going to rearrange this. I'm going to get V2 is equal to P1V1 over P2. And now I just want to plug and chug. Now it doesn't matter which one I set as 1 and which one I set as 2. What does matter is that I link this volume with this pressure and this pressure with the new volume that I'm looking for. So whether I look for V1 or I look for V2 doesn't really matter. What does matter is that these two stay linked and these two stay linked. Whether they're set as 1 or 2 doesn't matter. So here I'm going to let 25 liters be V1, which means the 1 atmosphere has to be P1 and my 1.5 atmospheres is going to be P2. So it's going to look something like that. I'm going to run that through my calculator. I'm going to get 16.6 repeating and 7 at the end. And of course, I'm going to apply my sig figs. Since I only get 2 sig figs, my final answer has to be 17 liters. All right, let's try this again. A balloon is filled with 73 liters of air at 1.3 atmospheres of pressure. What pressure is needed to change the volume to 43 liters? All right, so once again, we'll start with P1V1 is equal to P2V2. And again, one thing you can do to keep track of this is you can just make a little list. That tends to help people. P1, V1, P2, V2. Some equal signs here. And we can just go through the question and pull these things out. All right, so balloon is filled with 73 liters. I'm going to let that be V1, 73 liters of air at 1.3 atmospheres. So since I let that be V1, that has to be P1. We're going to put that in atmospheres. And then it says what pressure, so I'm going to be looking for P2, that's my unknown, is needed to change the volume to 43 liters. That's going to be my V2. All right, so I'm looking for P2, so I'm going to say P2 is going to be equal to P1V1 divided by V2. And now I'm just going to plug and chug. P1 we said was going to be 1.3 atmospheres. We're going to multiply that by V1, which we said was 73 liters. And then we're going to divide that by V2, which we're told is 43 liters. Then I'm going to get out my handy dandy calculator, which happens to be my cell phone. And we're going to take 1.3 atmospheres times 73 liters, divide by 43, and we get 2.206976. However, I only get 2 sig figs, so I'm going to stop at 2.2 atmospheres. And here we can see liters will cancel out. We'll be left with unit atmospheres, which tells us we're probably on the right track. The other thing we can look at with these problems, this is what's nice about gas laws, is that we can see that our volume decreased. Now we know that these have to be inversely related. So if the volume went down, we would expect the pressure to go up. And so did our pressure go up? It did. It went from 1.3 atmospheres to 2.2 atmospheres. So again, gives us a little bit of feeling of, yay, we did this right. All right. The next thing we want to look at is Boyles Law. Now, Boyles Law tells us that the volume of a gas is directly proportional to the Kelvin temperature if the pressure is held constant. So Kelvin then, Kelvin is a pain, but you got to be in Kelvin whenever you're working in gas laws. In fact, anytime you need a temperature with gas laws, I recommend you're in Kelvin. Typically, you have to be in Kelvin anyway, and then you can always change back to degrees C. There's only like one time, one instance when you can be in degrees C and it'll still work out. I'm not going to tell you when that is because Kelvin works every time. And then all you have to do is convert back to Celsius at the end of your problem. Kelvin is equal to degrees C plus 273. Okay, so that's what we need to do to get Kelvin. So a lot of times in the lab, we will be in degrees C. So we need to take that degree C, add 273. That gives us our Kelvin temperature. With the Kelvin temperature, we'll then do the math calculations. And then if we need to, we'll convert back to degrees C to answer the question that was originally posed. All right, we're going to see kappa come back into play again. And again, just like with Boyles Law, the kappa really doesn't matter. It's some constant. Here we know that these guys are going to be proportional. So as one goes up, the other goes up in proportion to it. And it's based on the Kelvin scale. That means V over T is equal to kappa, which means we could say V1 over T1 is equal to V2 over T2. That tends to confuse students. I've learned through the years that the better way to represent Charles' law is V1 T2 is equal to V2 T1. This way you don't get the inverse of the answer. It's lined up for you so that you have the volumes and the temperatures on the top line rather than in the denominator. All right, let's take a look at some problems for this. What is the final volume of a gas that starts at 8.3 liters and 17 degrees C? And we're going to heat it to 96 degrees C. So again, we're going to start with V1 T2 is equal to V2 T1. And of course, I'm going to make my little list. So I'm going to have V1, T1, V2, T2, T2. There we go. So what is the final volume? So final volume is what I'm looking for of a gas that starts at, so that's going to be 8.3 liters and 17 degrees C. And it's heated to 96 degrees C. Now remember, this only works in Kelvin, but they gave us C. That's pretty common. So what I'm going to do is convert both of those to Kelvin. So 17 plus 273 is going to be 290. And then 273 plus 96 is going to be 369. Now these are not degrees, it's just Kelvin, so it's just a K. We don't say degrees Kelvin. Who cares? If you do it, I'm not going to take points off for that. So if you give me a degree K, I'll laugh at you behind your back. All right. V1 T2 is equal to V2 T1. We're looking for V2. So V2 then is going to be equal to V1 T2 divided by T1. Now I'm going to plug and chug these in. We got 8.3 liters. We're going to multiply that by T2, which is 369 Kelvin. And then we're going to divide that by T1, which is 290 Kelvin. And of course, I'm going to do this in Kelvin. I'm going to do this the right way. If you don't believe me, you can feel free to do it in degrees C and see if you get the same answer or you get a different answer. I'm going to put my money on a different answer. But sometimes we just have to try it to prove it to ourselves, so go for it. All right, so we have 8.3 liters times 369 divided by 290 gives us, how many sig figs do I get here? 2, 3, 2. I'm going to apply 2 to my answer, which gives me 11 liters. Final answer. All right, now, is it right? Okay, let's see. What is the final volume of a gas? We heated it up. So if we heated it up, it should have expanded, which means it should have gotten larger. Did it get larger? And it did. It went from 8.3 to 11. So we're on to something there. We're cooking good with gas. All right. What is the temperature of a gas that is expanded from 2.5 liters at 25 degrees C to 4.1 liters at constant pressure? Now I'm going to say, what is the temperature? And I want this in degrees C. My final answer in degrees C. So this question doesn't actually pose itself that way, but I'm going to add that little piece in there because typically on an exam, I'm asking you for the degree C temperature, not just any random temperature. All right, so V1 T2 is equal to V2 T1. First thing we're going to do, we're going to convert, right? 273 plus 25, that's going to be 298 Kelvin. All right. Now we're looking for what? We're looking for T2. So T2 is going to be equal to V2 T1 divided by V1. So V2, we're told is 4.1 liters. We're going to start at 298 Kelvin. We're going to divide it by 2.5 liters. All right, so 4.1 times 298 divided by 2.5. 2 sig figs gives me 490 Kelvin. But we want our answer in degree C. So we're going to take 490 minus 273. 490 minus 490 minus 273. Having some finger issues here. All right, that gives us 217, which will have to be 220. Only get 2 sig figs. Got to go to the tens place in the subtraction. Degree C. Final answer. All right. So again, hopefully you're seeing Charles' law sets up very much like Boyles' law. Just got to keep track of the P1s, the T1s, the V1s. It gets a little confusing. So just trust your subscripts. Make sure you're using them or else you'll really get confused. Again, you can make that list down the side. I've been doing this for years, so I tend to get away from it after a while. But if you make the little list down the side, typically that helps you keep things straight. You don't need to memorize the formulas, obviously. That'll be either provided on the exam or you can have it as a cheat sheet on the side. So don't worry about memorizing formulas. But what I tend to tell students is you don't need to memorize formulas. I've always been that way. But you're not ready to take the exam until you know the formulas. So don't make flashcards. Just keep doing problems. The more problems you do, you'll end up knowing the equations inside and out, and that means you're probably ready for the test, and there's not going to be much I'm going to throw past you without giving you some work. Most of the questions I'm going to ask will be very similar to this for this section, so you'll knock these problems out without any problem at all if you have been practicing. Gay-Lussac's law is going to bring home the same idea here, so it's the third verse is same as the first. Except what he was saying was that the temperature and the pressure of a gas are directly related at constant volume. So we had constant temperature, then we had constant pressure, now we have constant volume. So P equals some kappa times T. We can rearrange this, rearrange that, finally get to a useful equation, P1T2. So now we're just substituting in pressure in place of volume. So one little caveat to this that's different than Charles' law is remember we have 2 units for pressure. So you got to keep track of ATMs as well as mmHg. Once you have the same unit though, these problems are going to fall out just like the last 2 sets. So what is the pressure inside a 0.250 liter can of deodorant that starts at 25 degrees C and 1.2 atmospheres if the temperature is raised to 100 degrees C? Now, here we see, and I've warned you off the start, and once we get to gases, the idea of useless information comes out, and there it is. Okay, there is some useless information here. Now with gas laws, there are 4 variables in gas laws: pressure, temperature, volume, and last but not least is moles. Now we won't see moles until next, right? So far we've only been looking at these 3. Now that means when you make your list, what you could do is just get into the habit of going P1, V1, T1, and then P2, V2, don't know if it's going to let me write it down here. Nope, it's not. Was right way over here, T2. Okay, so now we can just look these up in the question. Now, in this case, we already know because we're practicing what it is I'm lecturing, and we know we're looking at Gay-Lussac's law. So we know we're looking at pressure and temperature, which means we know just starting out on this problem that the volume is going to be useless. All right. Now, let's pretend like we didn't know. So it's quiz day, it's test day, you're sitting down in front of your computer, and you're taking this assessment. And you don't know exactly what I'm targeting with each question because it's just popping up randomly and you're just trying to do these problems. So you read the problem and you start filling it in. So pressure 1, so let's see, what is the pressure inside? Okay, so we're going to be looking for P2. All right, and it's going to start at 25 degrees C, so that's going to be T1. And 1.2 atmospheres, that's going to be P1. And of course, we're told that the can is 0.250 liters. So I'm going to go ahead and fill it in, right? So that's it. That's the starting position of the can. Now, the temperature is going to raise 100 degrees C. And I'm looking for pressure. It doesn't mention the volume at all. It doesn't say the can exploded. It doesn't say the can, crushed in, collapsed. It doesn't say anything like that. So really, based on the question, what is the assumption that Mr. Caro has to make? That V2 must be equal to V1, and the can's volume didn't change. That's the only assumption we can make. So that means I don't need to worry about this anymore because V1 is equal to V2, then it's just going to cancel out in the equation. So now I know I'm looking for P and T. So we're going to have P1, T2 is equal to P2, T1. And here I want to look for the final pressure. So P2 is going to be equal to P1, T2 divided by T1. Now remember, these temperatures, much like Charles' law, they need to be in Kelvin. So that means this is going to be 298 Kelvin. And this one's going to be 373 Kelvin. So P1 then is 1.2 atmospheres. T2 is going to be 373 Kelvin. And T1 is going to be 298. All right, again, now it's plug and chug. So we got 1.2 times 373 divided by 298. That gives me 1.5. We're going to get 2 sig figs here, so 1.5 atmospheres. Now temperature went up. What should happen to pressure? It should also go up, and it did. So it looks like we're doing well here. All right. Last thing we're going to do then for this segment is put these pieces together. So actually, I think we'll end the segment here. It's been 23 minutes. You can play with those 3. And we'll start the next segment off by putting these things together. So now we're going to look at combining all 3 gas laws. So we're going to take Boyles Law, Charles' Law, Gay-Lussac's Law, turn it into one thing, which we're going to call the combined gas law. All right, so stay tuned for segment number 3, and we're going to tackle the combined gas law.